Alright, this is Unit 8, Simple Harmonic Motion, Topic 3. And for this topic, I am describing the relationship between uniform circular motion, shown here, and simple harmonic motion, shown here, and then calculating the period and frequency of a mass spring system in simple harmonic motion down here. So the relationship between simple harmonic motion and uniform circular motion can pretty much be described as this. Uniform circular motion is in two dimensions, the y and the x, and in uniform circular motion, the angular velocity is constant, and the angular displacement is related to the angular velocity by the equation theta equals omega times t, where theta is the angle in the x or y of the x or y. So plugging this into the x and y positions makes it clear that these are the equations giving the coordinates of the object at any point in time, assuming that the object was at the position x equals r on the x-axis at time equals 0. So you can find where the particle will be located in the circular path by the equation x equals r cosine omega t, where r is the radius, which is the farthest distance it will be from the center of its uniform path. So how does this relate to simple harmonic motion? Well, an object experiencing simple harmonic motion is traveling in one dimension, as you see here, and its one-dimensional motion is given by the equation x equals amplitude cosine omega t, where amplitude is the maximum displacement of the object from its equilibrium position. So basically, it's the same equation applying to the position of an object experiencing simple harmonic motion and one dimension of the position of an object experiencing uniform circular motion. And this omega, found in both locations, or equations, is known as the angular frequency. It's the symbol for angular frequency, which is inversely related to period, which will be discussed in the second half of the video when we're calculating period and frequency of a mass spring system, which we're going to do now. So to calculate the period of a mass spring system in simple harmonic motion, you need to have the mass and the spring force constant. So it can be found by the equation. If you have those two things, it can be found by the equation period equals 2 pi times the square root of mass over spring force constant, or spring constant. So let's say we have a mass of 150 kilograms and a spring constant of 2 times 10 to the 4th newtons divided by meters. We plug that into the equation. T equals 2 pi times the square root of 150 divided by 2 times 10 to the 4th, and we find that the period is equal to 5.44 seconds. So that is the amount of time it takes for one full cycle to be completed of the simple harmonic motion. So then frequency, which is inversely related to period, as you can see right here, would then just be 1 over period, since that is the definition of being inverse. We take the period, 0.544, put that, or we take 1 over the period, which which is 1 over 0.544, and we find that the frequency is equal to 1.84 hertz. And that is the frequency of this object in simple harmonic motion, given the conditions that it's 150 kilograms and the spring constant is 2 times 10 to the 4th newtons divided by meters. So that is Unit 8, Simple Harmonic Motion, Topic 3.